So here are some examples of how you use this theorem. So differentiate the following functions. And these are all going to be area functions. And by area functions, I mean functions that measure area and the parameter ends up being one of the endpoints of the area that you're measuring. Okay, so the first example is going to be the function g of x, and it's going to be the definite integral from 0 to x of the square root of 1 plus t squared with respect to t. So this is the area under the graph of the function f of t is the square root of 1 plus t squared between 0 and x as your left and right endpoints. So obviously that's going to depend on x. So whatever x is going to determine what this area is, and that's how this actually defines a function, g of x. Your second one will be h of, oops, I wrote the wrong letter. H of x is going to be the definite integral from 1 to x of sine of pi t squared over 2 with respect to t. That's a complicated function, right? Pi t squared over 2 plugged into sine. That's no laughing matter, but we can still handle it with the fundamental theorem of calculus. In part C, I've got function f of x now, and it's going to be defined as the definite integral from x to 0 of e to the t squared with respect to t, and then finally the last one, q of x. I don't think I have enough room to write it here. Let me scratch this out and start it down a little bit lower. Q of x is equal to the definite integral from x to x squared of the square root of 4 plus t dt. So those are the four functions we're going to differentiate. Pardon me here with the scribbles. Hope that isn't distracting. But let's work these out. So the first one, we're going to take the derivative of g of x, so g prime of x. Now I really encourage you to write out some of these extra steps that I'm going to show you for the first few examples. You don't have to do these all the time, but this is actually a fairly tricky concept for a lot of people, and one of the ways you can make it harder on yourself is to not show all the steps. So if you prefer to do that, you go right ahead, but I really urge you to follow my lead here and draw out all of the steps of these solutions. So the first step I'm going to do, I'm just going to use different notation to say the exact same thing. So I'm not actually changing anything here. I'm not actually calculating the derivative just yet. I'm just writing the derivative of g of x in different notation. That's supposed to be a 1. That was an accident. Okay, so that's the derivative with respect to x of g of x, right? This is literally g of x written in here, except my 1 is a bit weird looking, but that's g of x. And why is it that I bother to write it this way? Well, because then you can copy this visual way to apply the fundamental theorem. It just says that the derivative is going to cancel with the definite integral, and the x is going to fall in place for the t. And then what you get is everything else disappears and you get 1 plus x squared. And then you're done. So it's actually fairly quick in the sense that the fundamental theorem of calculus is actually doing all the work. Let's do part B here. And I'm going to start part B over here actually just because the way things are angled, I think I can fit more on the screen this way, and I don't want to scroll down if possible because I want to keep this on the screen. So for part B, let's write h prime of x, and I'm going to do the same technique. I'm going to just take a step to actually just rewrite h prime of x, but with different notation. So I'm going to write this as the derivative with respect to x of the definite integral from 1 to x of sine of pi t squared over 2 with respect to t. That's just another way of writing h prime of x. I just put the derivative with respect to x, and then I literally write h of x inside the square brackets. And then now I'll apply the fundamental theorem, which says I can cancel this derivative with this definite integral, and the x drops in for the t as it did before. And what am I going to get? I'm going to get sine of pi x squared over 2. So again, notice in both of these examples, the constant that was the lower endpoint did not play any role in the answer, just like the lower endpoint a did not play any role in the outcome of this derivative in the fundamental theorem, which is stated up here. Okay, so those are the first couple of examples. Now part C, and especially part D, even to a greater degree, throws a little bit of a curveball at you. Things suddenly don't fit the exact form right away. It seems to be rotated. There we go. Maybe that's a bit better. So for part C, let's take a look at what happens. So we've got our function f defined up here, and we want f prime of x. Well, I'm going to start in the same way. I'm going to rewrite it as the derivative with respect to x of the definite integral from x to 0 of e to the t squared with respect to t. So now, don't go too quickly, because you might fail to notice the fact that actually this is different than the fundamental theorem of calculus. It's different than the form originally was. Unfortunately, I have to pull this out so I can pull it down in front. So in the fundamental theorem of calculus, the constant was the lower endpoint and the variable was the upper endpoint. And that's not what we have here. We have the variable as the lower endpoint and a constant as the upper endpoint. So this doesn't exactly fit the form of the fundamental theorem of calculus. But what we can do is we can take advantage of the properties that I just mentioned in the previous section, or previous part. One of the properties we have is that you can change the order of the endpoints as long as you just, at the price you pay is that you have to put a negative sign in front of the definite integral. So that's actually not going to cause us any problems. We just have to watch out for it. So I'll rewrite this as the derivative of negative the definite integral from 0 to x of e to the t squared dt. And then it still doesn't exactly fit the form of the fundamental theorem because that negative sign's there, but that's okay. Negatives, that's just a constant multiple. I can pull that right out of the derivative. That's properties of derivatives. I can say that's negative the derivative with respect to x of the definite integral from 0 to x of e to the t squared. Oops, I almost forgot my dt. And now I can apply the fundamental theorem, because now it fits the form perfectly. I can take the derivative of the definite integral sign, those cancel out, and the x drops in for the t, just like it did before. And now we still have e to the x squared, but now this negative sign that was out in front just gets put on there outside afterwards. So that's the result for part C. And part D actually throws another curveball at you. You can see that neither of the endpoints are constant. But there's a way to deal with that too, and it ends up not being any major problem as long as you are aware of the trick that's needed.